In chapter 2, we are going to talk about the motion. We are going to define the concept of distance, speed, velocity, and acceleration. Also, we are going to describe a horizontal motion, and we are going to also discuss what happens if the object is moving at constant velocity and what happens if the object is moving at constant acceleration. For this chapter, please complete the pre-lab 6 in your lab manual, page 107, and also complete the lab 6, which is distance versus time, and start working in the homework number 2. The branch of the physics that study the motion is called mechanics, and the mechanics is divided in kinematics and dynamics. Kinematic is the part of the physics that just describes the motion. Doesn't matter what is the cause that produces that motion. But the dynamic is the part of the physics that study the motion, taking into account what are the causes that produce that motion. Usually, the objects are moving because we apply some force. Yes, this is the cause that produces the motion, the force. But now we are going to concentrate in kinematics. Then what we are going to learn in this chapter is we want to describe motion, or we want to describe the motion of the objects that move in horizontal direction. Yes, like this example. Or if the object moves in vertical direction, or if the object moves in both directions at the same time, in X and in Y direction. Then in this case, in these examples, we had two-dimensional motion. And this is we are going to try to learn in this chapter. If we want to describe the motion of this car, or if we want to describe the motion of this ball, then what we need to know, how we can describe the motion of this car, how we can describe the motion of the ball, what variables we need to use to describe that motion. Then let's try to describe the object of this car. And this car is moving in horizontal direction. And we can describe the motion of this car if we know the distance the car moves, if we know how much time, how long the car moves from this position, from this point to this point. Then, in order to describe the motion of this car, we need to know the length, which is a distance, and the time. Remember, these two are two fundamental quantities. As distance is related to length, and time is the other fundamental quantity. And also, it's important when we are talking about the distance, then we can use the units of the distance that now we know. Can be feet, yes, if it's English system, can be meters if it's in SI system, or can be centimeters if it's in CGS system. Another units we also use are miles, inches, or kilometers. And time can be seconds, can be hours, days, years. Yes? Then we can describe the motion of this car based on these two fundamental quantities, distance and time. Now, what happens if we want to describe the motion of these two cars? Let's think this car starts moving from the position 0 meters, and they were moving. They start at 0, and they was moving the same time. Then now, how we can describe what happened with the car, with the blue car, what happened with the red car? Then now we need to use one more variable to describe, to compare the motion of these two cars. Then this new variable is the combination of the length and time. Then what we can say is the red car was faster. Yes, was faster. Then how we can describe, how we know the red car was faster? Was faster because was moved more distance, yes, the more distance in the same time. But the blue car moved less distance in the same time. And when we are talking about how faster is, then we are talking about the relation between distance and time. And this new variable in which we correlate length and time, or distance and time, is called average speed. Then the average speed is the ratio from distance to time. And the way we can write as an equation is like that. This small bar on top of the V is important because this means it's the average speed. It's just not the speed, it's the average speed, and equals to the distance over time. And now what is the units of speed? Because we had in the numerator distance, since the units can be, for example, miles, and in the denominator hours, then can be miles per hour. Can be kilometers is the units for distance over the units for time, then kilometers per hour, or can be meters per second, can be feet per second, centimeters per second, can be inches per second. Yes, all these are units of speed. Is always units, the distance or length, yes, divided by the units of time. Then we can define the average speed of the ratio between the distance traveled and the total time elapsed. Also, the average speed, or the speed, is the measure how fast the object is moving. Then now we can describe the motion of any object if we know the distance traveled, the time, and also the average speed. And in general, we can describe the motion of any object if we know the distance and we know the time. And for example, we can describe the motion of these windsurfers if we know the distance and the time, because if we know the distance and the time, we will know also the average speed. Then now we can describe the motion of any object if we know the distance traveled and the time elapsed, and these are fundamental quantities. Or also, then if we know the distance and the time, then we can use another quantities to describe the motion. And how we can get that quantities? We combine the length and time. And one of these is the speed that we already discussed. But also there are another two quantities we want to know, is velocity and acceleration. And let's now try to define what is velocity and what is acceleration in terms of the distance and the time. Then this is just the review. What is the average speed? Is the distance traveled and divided by the time elapsed, and is the measure how fast the object is moving. And this is the equation we can use to calculate the average speed. Before defining the concept of velocity and acceleration, let's describe the motion of the objects at constant speed. And we had this car that is moving in this distance. Then we want to calculate what is the average speed in the first segment from 0 to 10 meters, in the second segment from 10 to 20 meters, and in the last segment from 20 to 30 meters. And let's try to calculate that. And we know the average speed equals to the distance over time. Then for the first segment, yes, we had for the red line. Then we had, in this case, the average velocity equals to distance will be 10 meters divided by time. The time from 0 to 1 second is 1 second. Yes. Then the average speed will be 10 meters per second. Then let's try what happened in the second segment. What is the average speed in the second segment? Then we had this car moved from 10 meters to 20 meters. Then in this, for the second segment, the distance that the car traveled correspond to 10 meters. Yes, 10 meters is 20 minus 10. Maybe I will write here that. With the distance correspond to 20 meters minus 10 meters. Divide by, now 2 seconds minus 1 second is 1 second. Then we can see the average speed will be 10 minus 10 is 10, divided by 1 is 10, then 10 meters per second. And we will do the same in the last segment, will be 30 meters minus 20 meters, and 3 minus 2 seconds will be 1 second. Then the average speed is 10 meters per second. Then what happened is we can see the average speed in each segment is 10 meters per second. Is 10 meters per second. Means this car was moving at constant speed. Yes. Then how we can describe how we know the object is moving at constant speed? What we can see is the car is traveling equal distance, yes, 10, 10, 10, in equal period of time, 1 second, 1 second, 1 second. And now we can define if the car is moving equal distance in equal period of time, then that object is moving at constant velocity. And this is one way we know if the object is moving at constant speed. Yes, is always the same speed. If the object is moving equal distance in equal period of time. And let's try to see what happened with the motion of this car. Yes, this car was moving from 0 mile to 1 mile, then to 2 miles, then 3 miles, then 4 miles. Let's see what happened with the time. For the first mile, the car spent 1 minute. For the second mile, the car spent 1 more minute. Yes. For the third mile, the car spent 1 more minute. And for the 4th mile, the car spent 1 more minute. And we can see this car was moving equal distance 1 mile over equal period of time. Yes, 1 minute. Always 1 mile, 1 minute, 1 mile, 1 minute. Then without calculate the average velocity by the graph, we know this car is moving at constant speed because covered equal distance in equal period of time. And now what will be the average speed? And the average speed will be the distance, which is 1 mile, divided by the time will be 1 minute. Yes, then it's 1 mile per minute. Another way we can express this one, yes, is the same thing, yes, because we had 60 minutes in 1 hour, yes. Then we can say also, and we are saying the same thing, the average speed of this car is 60 miles per hour. If this car is moving at constant speed because it's always the same, it's not going to change, then sometimes when we are talking about the constant speed, then we can say the average speed equals to, just we can use only in the case when the when the car is moving or the object is moving at constant speed, because it's always the same, then the average speed is equal to constant value. Then sometimes in the books you will see you don't need, if the velocity is the speed is constant, you don't need this bar. Why? Because it's always the same. Then it's 1 mile per minute. Yes. Then the average speed equals to a constant value. Then let's try now to solve these two problems. These are really simple problems, but it will help you to know how to deal with the units, with the significant digits, and the equation. And in the first problem, we had a car that travels 150 kilometers in 3 hours. Then we need to find what was the average speed. Because we know the distance, we know the time, then we can calculate the average speed just applying the equation. And if we apply the equation, we will have the average distance will be 150 divided by the time, but the time is 3.0 hours. And the average speed will be 50. And now the units, very important, don't forget the units. And these are the units of the speed. Then we know we are doing correctly. Yes, it's units of distance divided by the units of time. Because we had two significant digits, top two significant digits in the denominator, then here we want to write we had two significant digits, and this is the answer. Always we need to give the answer of any quantity, the number, and the unit. Always we want to express the answer like that. In the second case, we know the average speed of the car is 50. Here is the average speed is 50 kilometers per hour, and the time travel is 2 hours. And we want to know what was the travel distance. We need to find the distance. In this case, because we had units time involved in both quantities, the first thing we want to check if the units are consistent. Then we had kilometers per hour, we had hours here, then we can see the units are consistent, then we don't have problem with that. And the next thing is we want to identify what equation we can use. Then, because we know the average speed, we know the time, we know this is the equation we can use to calculate the distance. And now the next thing is we want to solve for the variable. To solve for the variable we need to find, yes? We need to calculate. Because we want to solve for the distance, we need to get the distance of d by itself. Then we multiply by time on both sides. It's cancel out. Now the distance equals to average. Usually in the books, first is the average speed and then the time. Then this is I am writing like that. Then now just we need to replace the values and get the distance. Then the average speed is 50 times 2.0 hours. Then one thing we need to be careful is with the units. Because it's a distance, we know the units we expected is kilometers in this case. And let's see, this cancel out with this one, and this is the units we expected, which is kilometers, then it's right. And 50 multiplied by 2 will be 100 kilometers. And it's okay, we had here one significant digit, here with 2, then we must keep one significant digit. And this is the answer. In this example, we had this situation. The driver of a car moving at 72 kilometers per hour drops a road map on the floor. It takes him 3 seconds to locate and pick up the map. And how far did he travel during this time? And the first thing we want to find is the information from the problem. This is the first thing we want to get, the information. Then what we know is this car was moving at 72.0 kilometers per hour, and this was moving at this during 3 seconds, and he was moving at this speed during these 3 seconds, and we can consider this is the average speed, and he traveled at this speed during time equal to 3 seconds. And what we want to know is we want to know what was the distance, how far did he travel during this time. Then we want to know what was the distance he travels during this time at this average speed. Then we know the average speed equal to 72 and the time 3.00 seconds. And let me write here time with the correct number of significant digits. Then we know if we had the average speed and we know the time, then we can calculate the distance using this equation. But before to calculate the distance, we need to check if we had consistent units. Are the units consistent? Then the answer is no, because we had here kilometers per hour and here we had seconds. Then we need to do something to get consistent units. Then just to practice, let's try to convert kilometers per hour into meters per second. Now, this is we learned in the previous section how to do that. And what information we need? Yes, we know 1 kilometer equals to 1,000 meters. And also, maybe we can use this one directly. 1 hour is 3,600 seconds. It's 60 times 60. This is why it's 3,000. 1 hour is 60 minutes. 1 minute is 60 seconds. And we can use directly this one. Then 72.0. And let's convert first third one. We can also convert kilometers per hour into kilometers per second. Yes, because what we had problem is with the units, the time units, which are different. But let's convert this one into meters per second. Then here we had the right way to write the conversion factor. Yes, is the only way this cancel out, and we have meters here. The next thing, we want to convert hours into seconds. Then 1 hour, and we know hour must be on top. The only way we can cancel out the hours if the answer is in seconds in the denominator. Then this cancel out, and we had meters per second. And finally, we had this one is 72.0 times 1,000 meters, and we had here 3,000 seconds. And if we just multiply 72 times 1,000 and divide by 3,600, we will get 20.0 meters per second. Remember, we had we don't need to take into account the significant digits of the conversion factor. If the number we want to convert has 3 significant digits, the answer we got must be also with 3 significant digits. And this is we had here 20.0, and here will be meters per second. Now we had consistent units, then now we can calculate the distance. Then now let's calculate the distance. Then now we had the average speed equal to distance over time. Because we want to solve for time, we multiply both sides, then we will have distance equals, and let's write in this way, yes, this is the way it appears in the books. Then the average speed is 20.0 meters per second multiplied by the time. Time is 3.00 seconds. Let's do like that. Then we expected the answer in meters because it's distance, this is a length. Then the seconds must be cancelled out, and this we can see the seconds cancel out as we expected. Then 20.0 times 3.00 will be 60.0 meters. And we had 3 significant digits, 3 significant digits. We want 3 significant digits in the answer. Then the answer in this case will be 60.0 meters. Then now let's talk about the velocity. Then when we say a speed, is describe how fast some object is going. But if we want to describe the direction, is where the object is going. Then when we describe both speed and direction, then we are talking about the velocity. Then one example of the speed can be 50 kilometers per hour, but one example of the velocity will be 50 kilometers per hour due west. Then when we are talking about the velocity, we are talking about the number, yes, the number, and we call that the magnitude, but then also we are talking about the direction. If in physics any quantity that to describe that quantity we need the number and the direction, means when we need to the magnitude and the direction, then we call that quantity vector quantity. And this is why the velocity is a vector quantity, because that the velocity describes both direction and speed. If we don't need the direction to describe that quantity, we will say that quantity is a scalar quantity. For example, speed will be scalar quantity. How we can represent a vector? And to represent a vector, we can use an arrow, and the length of the arrow indicate the magnitude, the number of the vector, and the arrow's head indicates the direction. For example, in this case, we had these two cars. The first car is moving at 30 kilometers per hour in east direction. And the second one is moving at 60 kilometers per hour in east direction. And these two cars, they are moving in the same direction but with different speeds. If we compare the velocities for these two cars, this is moving at 60 kilometers per hour in east direction, and this one is moving at 60 kilometers per hour in northwest direction. We can see these two cars, they are moving at the same speed but in different directions. Then, just to review, when we are talking about the velocity, we are talking about the speed and the direction, or the magnitude and the direction. But when we are talking just the speed, we are talking about the number, as the number. Of course, always the number must be along with the unit. Yes, with the, in this case, the unit of the speed. And let's here review about in physics, we have two different quantities. One is scalar quantity, the other is the vector quantity. When we are talking about the scalar quantity, just we are talking about the magnitude, just the number plus the unit. When we are talking about the vector, then we need the magnitude, number plus unit, and direction. And here we have few examples that we don't need to give direction to describe that quantity. One of these is time. We know now speed, mass. Yes, we say 5 kilograms. We don't need to describe that quantity. We don't need any direction. Length, distance, area, volume, density. And here we had few examples of the vector quantities. Is the displacement. In your book, they don't talking about too much about the displacement, but displacement is in order to know for what place you are going to move, you need to know the distance, but you need to know also the direction. And in that case, we are talking about the displacement. For example, if someone tell me, Nora, move 3 meters, then I had to ask in what direction, yes? In what direction I had to move, north, west, or to the right, to the left. And I need some direction to know exactly to what place I had to move. And that is we call displacement. Then also velocity, and we will see another vector quantity is acceleration and force. And this is we will describe later. How we can change the velocity. Yes, now we know we can change the velocity, include the magnitude and the direction. Then we can change the velocity if we change the speed. Yes, for example, if we are moving at 30 miles per hour and we increase the speed and then we move up to 60 miles per hour. In this way, we can change the velocity. Yes, we change the velocity. The other way we can change the velocity if we decrease the speed. Yes, if we decrease the speed, then we can change also the velocity. We decrease from 60 to 30 miles per hour. But the other way also we can change the velocity when we change the direction. Yes, when we are moving the steer wheel to left to the right, we are changes the direction. We are changing the direction of the velocity in our car. Then another way we can change, even if the value of the velocity is the same, the speed is the same, but if we change the direction, then we are changing the velocity. As this is the case, this car is, the speed is constant, is the same. Yes, the numerical value of the velocity is the same, the speed is the same, but the direction is different. Then we can change the velocity is just we change the direction. Also, if we change both, if we change the speed, means the magnitude, and if we change the direction. These are different ways we can change the velocity. And why we are talking about this one? Because when we change the velocity, what we say is we are accelerating something. Then how we can describe acceleration? Acceleration is the change of velocity per unit time. Yes, is the change of velocity. And again, how we can change the velocity? We can change the velocity if we change the magnitude of the velocity. Means we can accelerate if we change the velocity, the magnitude of the velocity, but we can accelerate also if we change the direction of the velocity. Yes. And here we had the 4 different ways we can accelerate the car. A car means the 4 different ways we can change the velocity per unit time. Then now we can define the acceleration, the change of velocity over the time. Yes. When we say change of velocity, yes, we say change in velocity, then means we start at some initial velocity and then we move to some final velocity. Then we can calculate this change like final velocity minus initial velocity divided by the time. And this is why we had this equation here. Yes. You can also write the equation like that, but here you can see clearly the acceleration is equal to the final velocity minus initial velocity divided by the time. Remember, acceleration means change in velocity, either magnitude or direction. Now let's see what happened with the units of acceleration. Then let's write here, we will discuss the units. Okay, then we had acceleration, and let's just discuss the units. When we discuss the units, we use this bracket. And let's see what units we had on top. Let's think in SI system. Then velocity, meters per second. As this is we had on top. As this is we had here, meters per second. What units we had in the denominator is time. Then in SI system will be seconds. Then now let's divide the units in the same way we divide numbers. Remember, this is the division line, yes. Then we don't change the first fraction. We change the division by multiplication and we flip the second fraction. We can write this one over 1, then this is 1 over second. And now we multiply in the same way we multiply fractions. Meters times 1 is meter, second times second is second squared. Then the units for acceleration in SI system is meters per second squared. And in the same way, we can see the units for acceleration can be meters per second squared, can be feet per second squared, can be centimeters per second squared, can be miles per hour squared, or kilometers per hour squared. And this is why we had square units in the denominator. And these are the units for acceleration. The next thing we want to describe is how we will know if some object is moving at constant acceleration. As we already now we know, now we can describe when an object is moving at constant velocity. Now we want to do the same in case of the constant acceleration. Then we had this information, we got this information, this car is moving. In the first second, this car moving from 0 seconds to 1 second, and the velocity was increasing from 0 meters per second to 10 meters per second squared. Sorry, 10 meters per second. From 1 second to 2 seconds, the velocity was changes from 10 meters per second to 20 meters per second. In the last second, the velocity was increases from 20 meters per second to 30 meters per second. Then one thing we can see here is what happened with the velocity. The velocity is increasing, yes, is increasing. Because the velocity is increasing, what happened with the distance that the car is moving in each seconds? The distance is not the same, yes, it's not the same. It's not the same. Then one thing we can see is if the object is moving at constant acceleration, cover different distance in equal times intervals. Yes. Then in this case, one of the way we will know if the object is moving at constant acceleration if cover different distance in equal period of time. Yes. Then this is one characteristic. Then let's now try to calculate what is the acceleration in each of these segments, the first segment, the second segment, and the last one. And what happened in the first segment? Then we had acceleration. Then let's do this part. Yes, then the acceleration in this part will be final. But final velocity will be, in this case, this will be the initial, this will be the final. Yes, for the first segment. Let me write here, this will be the initial, this will be the final. These velocities are the velocities just in this point. Yes, they are no average velocities. Are the velocities in this time, just in this position. Then it's 10 meters per second. 0 divided by the time will be 1 second. And we know the acceleration will be 10 divided by 1 is 10. And we know meters, seconds over second will be meters over second squared, as we did before. And we know now the acceleration in the first segment is 10 meters per second squared. And if we calculate the acceleration for the other segments, we will get the same answer. Yes. Then let's do for the other one, for the second segment, and let's now we will concentrate in this part. And in this case, this will be the initial, this will be the final. Then will be 20 meters per second minus 10 meters per second divided by 1 second. Yes, 2 minus 1 will be 1 second. Then will be 10 meters per second divided by 1 second will be 10 meters per second squared. And we can do the same with the last one. I don't think we need to do the last one. Yes, then 30 minus 20 is 10. Yes, divided by 3 minus 2 is 1 second. Is 10 divided by 1 will be 10 meters per second. Then what happened? What we can see is the acceleration is the same. Yes, is the same. Then the acceleration is constant. Yes, it's constant. Then why the acceleration is constant? And what we can see here in the case of the velocity is the velocity increases in the same rate. Yes, 10, 10, 10. Yes. Then this is why we can say if the increasing of velocity is the same in the unit time. Yes, 10 meters per second in 1 second. 10 meters per second in 1 second. The increasing is 10 meters per second in 1 second. Then the acceleration is constant. Then just to review, the velocity is constant if the object covers equal distance in equal period of time. But the acceleration is constant if the increasing of the velocity is the same in equal period of time. And if we just observe this graph, these two examples, what we can say, these objects are not moving at constant velocity. And what we know, because we had here the same time, yes, equal period of time, and the distances are not equal, then probably these objects are moving at constant acceleration because they are the distance they cover in the same period of time are not equal. Then probably these two objects are moving at constant acceleration. This is just to review. This is the definition of the acceleration. Always, if there is any change in velocity, either magnitude or direction, then the object is accelerating. Yes? This is why the acceleration is the change in velocity divided by the time. And these are the units. And let's now try to solve this problem. Again, these are simple problems, but it will help you to understand or to deal with the units and the equation. Then we had a bicycle that moved from rest to 5 meters per second in 5 seconds. Then what happened? That part is important. Yes, that part is important. Let's see if I can. When they say from rest, mean the initial velocity equals to 0. Yes. Then the initial velocity of this bicycle was 0. But after 5 seconds, the speed of this bicycle was 5 meters per second. And this is what we call final velocity. As in this problem, they are not giving the average velocity. They are giving some specific velocities. And we call this instantaneous velocity. This is the velocity just in one particular point. Then we want to calculate, it is from here to here. This is the time. And we want to calculate the acceleration. Because we know the velocities and we know the time, then we can calculate the acceleration. Remember, always the acceleration is the change in velocity over time. Yes, over time. And now we can calculate the acceleration equals to final velocity. Oh, another thing, we always need to check if the units are consistent, and they are consistent, no problem. Yes. Then will be the final over time, final 5 meters per second, initial 0, time 5 seconds. We know 5 minus 0 is 5, yes, and this is the same. We have 5 divided by 5 seconds. Then 5 divided by 5 is 1, and we know what happened with these units. Yes, we know we had meters per second, but then we flip this one. Yes, this is, and we had meters per second squared, and it's 1 meters per second squared. Then the acceleration is 1 meters per second squared. I want here to explain something. I want to write this one like 1 meters per second, 1 second. It's the same. Yeah? And when we say 1 meters per second squared, we say the velocity, yes, the velocity is increasing in 1 meters per second each second. Yes, this is why we had here second squared. Means the velocity, in this particular case, the velocity is increasing in 1 meters per second each second. as this is the meaning of 1 meters per second square. In this example, we had a car accelerates from rest at 5 meters per second square for 6 seconds. Then we want to know what is the final velocity of the car. And let's try to understand what is happening in this case. Then we had a car, and if accelerate from rest, we know the initial velocity equal to 0. And if the car accelerates means the velocity is not constant, yes? And this is why after 6.0 seconds, then we want to calculate what is the final velocity. If we know the acceleration of the car is 5 meters, its constant acceleration is 5 meters per second square. Then we know this is not the final velocity, and we know this is not the final velocity by the units, because we had here meters per second square, and we know this corresponds to acceleration. Then now we can calculate the final velocity. Then now we will check if we had consistent units, and yes, we had consistent units, we had seconds, then no problem. The next thing we need to know is what equation we will use to calculate the acceleration. Then we know the change in velocity corresponds to acceleration. Then this is the equation to calculate the acceleration. And we know the acceleration is 5.0 meters per second square. We know the initial velocity is 0. We know the time is 6.0 seconds. And we want to calculate the final velocity. And what we can do in this case, we had this. Let me write again the equation here. It will be easier. And we know the initial velocity is 0. Then we know this is 0. And when I write like that, means this term equals to 0. Okay? If this is 0, then finally we will have the final velocity over time. It's the same like if you had 5 minus 0, you will get 5. Yes, if you had the final velocity minus 0, you will get the final velocity. Then now it's easier to solve for the final velocity. Then to solve for final velocity, just we need to multiply by time. This cancel out. And usually in this acceleration is first, then is the time, but doesn't matter if you write times a or a times t, you will get the same thing. It's just in the books usually they write like that. Let me write better this thing. And now we can calculate the final velocity. Acceleration is 5.0 meters per second squared, multiplied by the time, which is 6.0 seconds. Then it's 5 times 6 is 30, and we want 2 significant digits. Now, we know the units we expected for the velocity is meters per second. Let's see this is the units we will get here. And these seconds cancel out with one of this one, then finally we have meters per second. And this is the answer. It's 30 meters per second. Just to get idea what is this velocity, this is about 60 miles per hour. Okay, you don't need to do this one, but just to get idea what is 30 meters per second. And we already discussed that we can calculate the average velocity if the object is moving at constant acceleration using this equation. It's just we divide the distance divided by the time. We can use the same equation if the object is moving at constant velocity, but what we are going to find is the average velocity will be always the same. But in case of the constant acceleration, we will see the velocity is going to increase in the same number, yes, in the same ratio, in the same period of time. And this is why here increase by 10, then increase by 10 in the next second, and then increase by 10. We already discussed that. Then we can calculate the average velocity if we just divide the distance divided by the time. Then what we want to find another way, we can calculate the average velocity if the acceleration is constant. And here we know if the acceleration is constant, the distance traveled by the object, in this case by this car, in the same period of time will be different. Yes, this is why you see here. Then I don't want you to worry much about these numbers. Yes, I love these numbers, but we will later we will see how we can calculate these numbers, how we can calculate the distance if the object is moving at constant acceleration. And for now, just we will use these numbers to do the calculation. Then now we want to calculate the average velocity if we know the distance and the time. And let's try to calculate the average velocity for each segment. Okay, then let's calculate the average velocity for the first segment, for 0 to 5 meters. And in this case, the distance will be, for the first segment, the average velocity, the distance will be 5 minus 0. Yes, will be 5 minus 0 will be 5 meters. Yes, will be 5 meters. And the distance will be just 5 meters. And the time will be 1 second. Yes, it's 1 second minus 0 will be 1 second. 5 meters. And the average 5 meters per second. Then if the acceleration is constant, then we can also calculate the average velocity if we know the initial and the final velocity in this period of time. Then let's try to calculate the average velocity, and if we know the initial and the final velocity. And the final velocity in this case will be 10. Yes, this will be for this, and this will be the initial, this will be the final. Then with 10 minus 0 will be 10 meters per second. I will write all the numbers. Okay, let me write all the numbers. Will be 10, final will be 10 meters per second plus 0 divided by 2. Then the average velocity will be 10 divided by 10 plus 0 is 10. 10 divided by 2 is 5 meters per second. Then we can see we got the same answer. Yes. And let's calculate for one more segment. Maybe we can try it for the last segment. Let's try it for the last segment. And let me and let's try to calculate what is the average velocity for the last segment. Then let's use first the distance over time equation. And the average velocity distance, then it's 45 minus 20 will be 25. Yes, I will just write 25. I don't have here more space. Then it's 25 meters. Yes, it's 45 minus 20. Yes, the distance in this case will be 45 minus 20 will be 25 meters. Time 3 minus 2 is 1 second. Then the average velocity will be 25 meters per second. And let's try to calculate using the initial and the final velocity. And its final velocity, this will be the initial, this will be the final, then will be 30 meters per second plus 20 meters per second divided by 2. 30 plus 20 will be 50. Yes, 50 divided by 2 will be 25 meters per second. Again, 30 plus 20, 50 meters per second divided by 2, 25. Then here we can calculate the average velocity of any object that is moving at constant acceleration using this equation, but we can use just using this equation. And this equation works because the increments of the velocity are always the same. Then this equation works only if the acceleration is constant. And one more thing I want to emphasize here is we can see, because when the car is moving, the distance covered by the car in the same period of time are not the same as when the car is moving at constant acceleration. They are not the same. And in this case, what we can see is the distance is not proportionally to t. Yes, it's both increases but not at the same proportion. Yes, if this increased by 1, this increase in another proportion. Then we will discuss this one later. Okay, we will discuss this one in detail, but I just you be aware about that. And this happens if the acceleration is constant. Then the distance is not proportional to time when the acceleration is constant. And this is just to summarize. This is the other way we can calculate the average velocity if the object is moving at constant acceleration. And let's try to work this problem. Then we had a car that is moving at 25 meters per second, and this car comes to a stop, yes, in 10 seconds. And we had this car. Let's see if I can draw here. We had this car, and this car is moving at 25 meters per second. And then after 10 seconds, the car stop. 0 meters per second, just 0, yes. When the drive slams on the brakes. Then we know this 25 meters per second doesn't correspond to the average velocity. This corresponds in this case to the initial velocity, and this corresponds to the final velocity. Then we want to calculate how far did the car travel while stopping. When we need to calculate the distance, then we want to calculate this distance, and this is we want to calculate. And let's try to write here the information we know. We know the initial velocity, and let me write this one with the correct number of significant digits. Okay. This is final velocity is 0, time is 10.0 seconds, and we need to calculate the distance. Then now the next thing, and I will send you the equation sheet. You will have the equation sheet in which you will have all the equations. Then you need to decide what equation we can apply, we can use to calculate the distance with the information we had. Yes. Then to calculate the distance, we need the average velocity and the time. Yes, we need the average velocity and the time. Then, but this 25.0 meters per second is not the average velocity. This is the initial velocity. 0 is not the average velocity, it's the final velocity. Then what we can do is we can use these two values to calculate the average velocity using the equation we know. Yes, now we know we can calculate the average velocity. And in this problem doesn't say, but we assume the car is moving at constant acceleration. And now we can calculate the average velocity. Once we calculate the average velocity, we can calculate the distance because we know the average velocity and we know the time, then we can solve for the distance. Then in this case, to solve the problem, we need to apply two steps. First, calculate the average velocity and then calculate the distance. To calculate the average velocity, first we will apply this equation. Yes, this is the first equation, and then we will apply this equation. And let's calculate the average velocity first. Divide by 2. The final is 0 plus 25.0 meters per second divided by 2. Then 25.0 divided by 2 will be 12.5 meters per second. And we had the first part as we did, but now we need to calculate the distance. This is what we need to calculate the distance. And we know the average velocity equals to distance divided by the time. We need to solve for the distance, then we multiply by time on both sides. The distance, then we had distance equals to the average velocity multiplied by the time. Then it's 12.5 multiplied by the time, but the time is 10.0 seconds. And the units we expected in the answer is meters, and this is, if we cancel out the seconds, there's one on top, the other in the denominator, they cancel out, and we have the correct units. Then the final answer is 125 meters with 3 significant digits. Now this is then this car traveled during this 10 seconds 100, let me see, I can write here, 125 meters. Now let's talking about the graph. Then we know this is one of the equations we can use to describe the motion of the car of any object. Is the average velocity equals to distance over time, and we know if we multiply by t on both sides, we can get this equation. It's just we did this one in several examples. Then we can write this equation. Yes, we can write this equation as distance equals to average velocity multiplied by the time. in this graph, we had the distance covered for some object during some period of time. And when we plot this data, we can think that when we plot this data, we got a linear relation. If we had the experimental data and we plot that data, yes, and we got a line, a straight line, then we know distance and time, they are direct proportional. Yes, distance and time, they are direct proportional. Why? Because we got a straight line. And we know the general equation when two variables are direct proportionally is d in this particular case, because d is y and t is time. Yes, we had d in y-axis. We had here d. Let me write here. Maybe I will write in that way d, and here we had time. Yes. Then is d equal to constant of proportionality multiplied by time. And we know the constant of proportionality equal to slope. And we already discussed this one in the previous chapter. And if we want to know the equation that correlate distance and time, then what we need to do, we need to calculate the slope. Yes, this is we did before. Then we need to calculate the slope. To calculate the slope, we will select 2 points on the line different from the experimental data. Yes. Then we can calculate the value of the slope. And in this case will be, let me try to write here, we had here, we had 440. Yes, this is, we had here 440. And in this case, we had 220. And if we, let's calculate the slope here. Let me write here the general equation for the slope is y2 x2 minus x1. And in this particular case, with the slope will be 40. If we say this one x is y2, yes, this slope, if this is y2, will be 40 minus 20. 40 minus 20 divided by 4 minus 2, x2 minus x1, that is 4 minus 2. And we say we have to be careful, always we need to write the units when we calculate the slope. And what are the units for y? Y is this. Let's ask, this is y is miles. What are the units for x? Hours. We need to write that. Then now we can see here is the calculation. 40 minus 20 is 20 miles. 4 minus 2 is 2 hours. 20 divided by 2 is 10 miles per hour. Yes. And this is why the slope is 10 miles per hour. Then now that we had the slope, we can write the equation that correlates distance and time. This is the general equation, yes. But now we know the slope means the k value is 10. Let me write this number, 10 miles per hour. And now we can rewrite the equation. You say distance equal k value, means the slope is 10 miles per hour, and then time, yes, time. And this we call the experimental equation. And this is the experimental equation because it's the equation we got from the data. And let me write here, this is the experimental equation, okay? This is the data we got from the experiment. Now, what happened if we observe the units, yes, the units miles per hour? We know this corresponds to some speed. Yes, by the units, we know this corresponds to the speed. Now we know this equation. This is the theoretical equation. This is the equation we know from the theory. Yes, we study in just now this one. And this is the equation from the theory. We call the theoretical equation. If we compare the experimental equation with the theoretical equation, what we can conclude? You see, distance, time, then 10 miles per hour must be the average speed. Yes. If we compare the experimental equation with the theoretical equation, 10 miles per hour must be the average speed. Then always, if we plot distance versus time and we got a straight line, means distance is direct proportionally to the time. And in this case, the slope corresponds to the average speed. Then how we can calculate the average speed? Just we need to calculate the slope of the line. Yes, just we need to calculate the slope of the line. But this happens only if the distance is direct proportionally to the time. Then this happens only if the car is moving at constant speed. Okay, this happens only if the car is moving at constant speed. The distance is direct proportionally to the time. Okay. Then let's try to summarize. And let's try to summarize what we studied today. Then let's see how we can describe the motion of this person in the different situations. In A, what happened? The person is standing still or is at rest, is not moving. Yes. What happened in the second case? What happened in the graph B? And we can see that person is moving in equal distance in equal period of time. Then we can tell that person is moving at constant speed. Yes. What happened in the graph C? Then what we can say is the person is not moving at constant speed because she's covered different distance in the same period of time. Then what we can say is that person is accelerating. This is one possible answer. We can say also that person is speeding up. Yes, is not moving at constant velocity. In case of the D graph, what we can say? We can say that person is not moving at constant velocity, at constant speed. This person is slowing down, yes, and also we can say is decelerating. Then this we can describe. Now you are able to describe the motion of the objects. Then just to remember, the acceleration is defined the rate of the change of the velocity. Then in physics, when we are talking about the accelerating or decelerating, we use always the same word, acceleration. The acceleration is related to both. And when we can say in the case of C and D, that person is accelerating. When we say accelerating, is we are talking about both acceleration or deceleration. Okay. I think this is all I had to discuss in this case.